see. All right, it's time again. So here's what I think we should do today. First, we do have a couple more problem sets left over from chapter 1, which we should go over. So let me get those open. Let's see. This is part 1 we've done. We still need part 2 and 3. Let's see. Actually, before we do that, I always like to check Moodle just to make sure everything's up to date. All right, here we go. So yes, we had yeah, we're all caught up here. So we've got I did post the solutions to last week's practice problems. Very good. Now for 2 and 3, we'll do that today, and then we'll start 2. Now 2 is a fairly long chapter, and we'll go through that today. If we do finish it somehow, I don't think that's going to happen, but you know, let me do this just in case. We'll post 3. 3 is actually long enough that it actually has 2 parts to it. Let's get those up there. This is where we start looking at other types of functions besides linear. So there's a 3a. And there's a 3b, which both of them have to be posted. All right, let's try that. So first I have to make sure the editing is on. Easy to forget about that. And all right, so now we're ready. Here's 3b. And 3a. Okay, like I said, I don't think we'll get to these today, but just in case, here they are. And so that way, today will primarily be the 2 problem sets and linear functions, and possibly 3a and 3b. So we'll just carry on with that. Chapter 2 also does have a problem set, by the way. So if we do finish chapter 2, we'll probably want to work on this one next week. Let me just open it up for a second. Yes, that's what I thought. Okay, so we'll probably be able to do these by the end of today. And if so, we'll have everybody work on this one for next week, but we'll figure that out as we go along. All right, so what we want to do now is grab the second rather problem set from chapter 1. Wait a minute. Oh, I'll just grab them from here. Okay, so, all right, we'll start here. And chapter 1, practice problems, part 2, this is the one. All right, great. So we'll do this one right now. And first, let me save it. Okay, what is today? 15th. Okay. Excellent. All right, so let's see. How would we handle these? Now, remember, what are we looking for? When we calculate the domain, we're basically trying to find any values that might cause either division by 0 or might result in us taking the square root of a negative number. Anything else will work. Now, what you might want to do before you tackle any of these problems, it might be easier if you can visualize what they look like. So why don't we get into the habit of looking at these graphs on Symbolab, which I introduced you to last week and the week before. And so basically what you can do is at least have a picture of this thing. And that way, I think it's easier to visualize what we're trying to do. All right, so let's see. This one was 1 over x squared minus x minus 6. All right, so on the graph, it should be clear if there's any holes, so to speak, in the domain, it'll show up as asymptotes. So for example, yeah, you can see there's 2 values of x that are going to cause us trouble. It appears that they are 2. Oh, wait a minute. No, that's not right. It looks like it's positive 3 and negative 2. Now, we can prove that in a very easy way. But yes, you see these red lines. These are asymptotes. And that indicates that this value cannot be substituted into the function. And so just looking at it, it appears to be, there's 2 of them. This one looks like 3, and this is negative 2. Now, how do you prove that? Well, what you want to do is look at that denominator, and you realize you have a quadratic function. And because of that, x squared minus x minus 6 can actually be broken down into 2 what are called factors. So how do you do that, by the way? What I'm going to do is show you what they are, and then we're going to figure out why. Okay, so for example, it turns out that this is equivalent to the product of x minus 3 and x minus 2. Now, the question is why? Now, you've probably seen this before, but I just want to remind you how this works. First, let's prove it. If you apply FOIL here, you'll see that here's f, here's o, minus 2x, here's I. Oh, no, sorry, my fault. What am I doing? This is plus 2. Sorry, this is plus 2. X, all right, let's try that again. So it's x squared for f. O is positive 2x. I is negative 3x. And finally, last is minus 6. So if you consolidate these, you'll get x squared minus x minus 6. So this is correct. Now, how does one normally go about factoring these expressions? Here's a way you can do it. If you look at these very carefully, whoops. What you'll notice is that if you were to, you're rewriting this as 2 what we call binary expressions. So why don't we try this? Let's just write this in general as x plus m times x plus n. And if you apply FOIL to this expression, you'll get first is x, outer is nx, the inner is mx, and then the last is mn. So you've got x squared plus m plus nx plus mn. So you're looking for you're trying to figure out what m and n are. So we know 2 things. First of all, this last term is negative 6. So therefore, m times n is negative 6. Now, there's only a handful of values this could possibly be. For example, if you multiply 1 times negative 6, or 2 times negative 3, or negative 1 times 6, or negative 2 times 3, any one of those pairs will give us a product of negative 6. But we note also that here, m plus n has to equal negative 1. So basically what we're saying here is we're looking for a pair of numbers whose product is negative 6, but whose sum is negative 1. So if you look at all the products, there's only one case in which their sum is negative 1, and that would be this one. Okay, so if you see that, if you say that m is 2 and n is negative 3, it's clear that m plus n is 2 plus -3, which is -1. At the same time, and m times n is 2 times -3, which is -6. So this is a general approach to finding factors. If you are able to do this with a different technique, or if you can just spot it by looking at it, that's great. But we can definitely prove that this denominator could be rewritten as 1 over, or the denominator is x minus 3 times x plus 2. So let's do exactly that. All right, so we have 1 over x squared minus x minus 6 is the same thing as 1 over x plus m. Now remember, m is 2, and x plus n is -3. All right, this is the key to the whole thing right here. And so if I were to set this equal to 0, or actually I don't have to set it equal to 0, what I'm going to notice here is that I cannot substitute either -2 or 3, because that would cause division by 0. You see what would happen if I put -2 in here, the first term will be 0. It won't matter what the second term is. I'll still end up with 0 in the denominator. Same thing with the 3. If I put 3 in over here for x, I'll get something times 0, which is still division by 0. So I cannot substitute either -2 or 3. That would cause division by 0, which we know does not work, and we know why, because of that cool video. So therefore, the domain is all real numbers except -2 and 3. So in our set notation, we can write that as the union of -infinity up to, but not including -2, -2, not, well, all right, this one is -2, 3. That means everything in between, but not including -2 and 3, and then from 3 up to infinity, not including 3. This is how it's formally written. So it basically is designed to show you that all the reals are included except for -2 and 3. Now, Symbolab actually is doing some of that too. In fact, if you look at it carefully, you'll see it's right there. All right. But the thing is, you have to understand, they didn't explain how they got it. All they did was they said, oh, here we go. Is this what you're looking for? So there it is. But now you understand why. All right. That's the key to the whole thing, the why. And because of that, any polynomial that you find in the denominator, you can often break it down into these factors, and then you can figure out more easily what the domain is. Now, sometimes it's trickier than others, but this one was very straightforward because it was a simple quadratic expression. Sometimes it, it can get worse than that. So yes, Fernando.
Sure, you can finish what you were saying and I'll ask my question.
Oh yeah, no, go ahead. I'm done.
Oh, okay. I just wanted to ask right there, like in the FOIL, when you're like right after, I noticed you used the M and N, those values, and I just wanted to ask, those were like just the values that you chosen, or from like, you know, something
No,
that's
they're
already
just meant
been
to
like.
be. It's just meant to make it a very general formula. M and N could be any two numbers. So I just wanted you to see that any quadratic expression can be decomposed into a product like this. The question is, what are the values of M and N? That's really what this is meant to show you. How do you choose M and N?
Okay, and it can't be like anything else, right? Like,
yeah,
you can't.
Their product is this. Oh, do you have another technique in mind?
No. I was just asking because like I was asking, would M and M just be like the only values you would use, or could you use like any other?
No, there's only one. It's unique. This M and this N are the only ones that will work.
Okay, thank you.
Right. If you try any other two numbers, you will not get the right answer. Okay. All right. Now let's try this one. Now 2 is a little simpler. You can see it's pretty straightforward what value could cause division by 0. Okay. So in other words, if you start with 4x plus 2, what number could cause that to be equal to 0? If you set this equal to 0, that means x is -1/2. So in other words, anything is allowable here except -1/2. That would cause an asymptote. So there is, in other words, there is an asymptote in the graph, but anything will be allowable except -1/2. So the domain is very simple in this case. It's just all real numbers except for -1/2. So again, the strategy is to simply look. Now, sometimes there is no value that leads to negative division by 0 or a negative square root, and then the domain is all the real numbers. We haven't seen that one yet. And again, if you want to confirm this, let's go to Symbolab. 3x plus 1 over 4x plus 2. And it should show up as a vertical asymptote at x equals -1/2. Let's take a look at it. And let's see, let's take a peek at the old graph. There it is. See, it's hard to tell sometimes from this, but that is equal to negative. Oh, there it is. No, wait. Sometimes they label it properly, and sometimes they don't. But yes, you can see from the graph, this is -1/2. And there's also horizontal asymptote, but we're not concerned about that because we're only interested right now in the domain. The domain only refers to the vertical asymptotes. Okay. Now, what about this next one? Ooh, we gotta have to watch this one. You can see because there's a radical. Whenever there's a radical, you have to worry about negatives. So first things first, it should be pretty clear that we can't have x equals 4. All right, so x cannot equal 4 because that will clearly lead to division by 0. But what about here? If I were to set x plus 4 equal to 0, I would get x equals -4. So what that means is that x can be -4 or greater. Because if I put a number in here of -4, we're fine. With the square root of 0. If I put, let's say 0, we're fine. So anything from -4 up is okay, but if x is less than -4, that would lead to a negative square root. Which is we're not allowing. So therefore, there's 2 gaps in the domain. So if you draw it like this, we can go down to -4. We can't have anything below that. So we can write this as everything from -4 up except for 4 itself. So what you often see in these graphs, you might see something like this. This is supposed to be a round bracket. And then here's another one that takes us up to positive infinity. So this is what we're trying to illustrate here is that you can have anything from -4, including -4, but not 4 itself. So this one's a little unusual. This is different than what we had before because it does not involve most of the negative numbers. But again, the square bracket is meant to indicate -4 is included. But this round bracket is meant to indicate 4 is not included. Okay. And the union, of course, we know what that means. So just out of curiosity, let's take a look at this in Symbolab. It's a very interesting looking function. I'm kind of curious to see. And, you know, it's something like this, unless you just do graphs all the time, it's very difficult to visualize what some of these look like. And that's why we have the technology. Let's see what that ends up looking like. It's not going to be pretty, I'm guessing. Ooh. Now that means it's thinking. There we go. That must have been a really bizarre function. Ooh. I figured as much. You see how it sort of looks like other functions we've had. The upper right-hand corner, you can see clearly x equals 1. Is that 1? No, I'm sorry, that's 4. Okay, that's the vertical asymptote, or the x asymptote, y asymptote. It means a function can't touch 4, and we knew that. But down here, normally this would continue, but we're forced to stop at -4. So that's why it looks so bizarre. So from -4 down, we're not allowed. And over here, we're not allowed to have +4. Now, again, it does show it's up here somewhere. You see how they've written it like I did. But again, this doesn't tell you why. Now, here's why this website exists, by the way. You see there's a million ads on it, which is, of course, normal these days. But if you were to pay for an annual subscription, you see how it says unlock steps? This is what they're hoping that you will do. You'll say, you know, I like this so much that I'm willing to pay for more details. So you pay them an annual fee, which I don't know what it is because I don't have it. And then like right here, they would go through it in more detail and show you all the steps that are missing. Here, they're basically just summarizing it for you. They're not really showing you where they got it. I don't really know what all this is for. This is not what we asked for, but they're okay, whatever. But yes, but the value of this thing is even if you don't pay for the subscription, you can always graph the function and take a look at it. And some of the things that you need could still be down here. And if you look over here, they've got all kinds of stuff like, oh, for pre-calculus, they figure these are the functions you'll need, but like what if you're doing simultaneous equations? They've set it up to make it easier for you to enter what you need. So it's kind of cool. But it's not completely free. Like I said, some of the most important details, you have to pay to see them, basically. It's kind of like letting you watch the first half an hour of a movie, just to make sure you really want it before you pay for it. But anyway, let's get out of here. I want to get back to where we were. There we go. Okay. Now what's next? Oh, now look at this one. You got two potential problems. Okay, so first things first, we got two radicals, which means there's two restrictions on our x that will help us avoid a negative square root as well as division by 0. So let's think about division by 0 first. If we allow x to equal 4, then we have division by 0. So that's clearly right out the window. But then we also have to avoid negative square roots. So if you look at this one, if I set this equal to 0, that means that If x is less than 4, then we have a negative square root. So in other words, let's say I put 3 in for x, I'll have the square root of -1, which is clearly not permitted. Now, as far as the numerator goes, what are we not allowed to do? Well, let's see. If I set this equal to 0, oh, whoops, sorry, that's 6. So therefore, anything less than 6, let's say I put 5 in here, I'm going to get a negative square root. So why don't we gather up all the numbers that we're not allowed to do? Okay. So I'm not allowed. Let's see what we can do here. Oh, so on this real number line, let's say I draw different number lines to indicate each of these restrictions. On the first one, the only constraint is 4. I can't do 4. Whoops. Okay, that's supposed to be a curved bracket. It lets me know not to include 4. Okay. Now for the second restriction, I must not have anything under 4. So look what happens here. So up here, actually, let me do this. Let me just change the color so you can actually see what I'm doing with these when I'm filling these in. So all of this is permissible. And so is this. But with the second restriction, I can have anything as long as it's not less than 4. So in other words, I can have this. And then the third restriction means that I can have anything from 6 and up. So where do they overlap? Well, here you can see that the one area they all have in common is that they all permit us to go from 6 and up. So if I restrict the domain to 6 up to infinity, I can never run into any problems. Okay, so I can't break any, like in the first thing, I'm allowed to have anything but 4, but 4 is not in this interval, so we're fine there. In the second case, I can have anything from 4 up, which certainly is okay here. So in other words, by consolidating all 3 of these, I can see clearly that I can allow for the domain to be 6 up to infinity, and none of these restrictions are violated. So if I were to plug, for example, 7 in here, I've got a positive exponent here, a positive numerator, I have a positive denominator, and I do not have division by 0. So this one was pretty challenging because you've got 3 restrictions. And so what we have to do is find the areas that they have in common. So that's how these are going to work. Now they do overlap, but we know for a fact that all 3 of them permit us to start at 6 and go up to infinity. All right, so let's go back to Symbolab, and we'll prove this, or let them prove it to us. Radical x minus 6, okay, over radical x minus 4, let's take a look. I wonder what this picture is going to look like. Again, I don't think it'll be pretty. Man, it's thinking. Okay, so you can see we did it correctly. The interval notation is everything from 6 up to infinity, including 6. But when you look at the picture, oh, that's weird. See, now that's interesting. I thought it was going to be a really strange looking shape, but it's actually pretty straightforward. But with the understanding that it starts at 6, so we can't have anything below 6. Well, that worked out rather well. Interesting. All right. So, okay, now these are different. These are the average rate of change. This is easy. Well, it is, well, let's just say, I shouldn't say it's easy. It's not as difficult. So let's do this. Let me make this a little bigger. What we have here is this. Think of this as A, and this is B. So we need 4 pieces of information. We have A and B. We need F of A and F of B. So in this case, F of A is F of 1, which is 1 squared, which is 1. F of B is F of 5. 5 squared is 25. Now, why is it F? Remember, the function is x squared. So what I'm doing is I'm squaring the A and I'm squaring the B. And so the formula that we need to calculate the average rate of change is right here. So I'll have 25 minus 1 over 5 minus 1. Okay. And that's it. That's all you have to do. So those are pretty straightforward. Okay. All right, everyone get that? All right, so let's do the rest of them. Now for root 6, we have f of x is x cubed. So what do we know? A is -4, B is 2. F of A means -4 cubed, -64. F of B is 2 cubed, which is 8. So therefore we have eight minus -64 over 2 minus -4, 72 over 6, which is 12. All right. So again, it was pretty straightforward. That's always nice when something's straightforward. All right, very good. Let's do the next one. So here we have f of, sorry, A is -2, B is 4. F of A, now this time f of A is a little bit more challenging because the function is a little bit more complicated. It's 5 minus 2 minus 2 squared, okay? So in other words, it's 5 minus 2x squared. So we'll end up with 5 minus 2 times 4, 5 minus 8, -3. F of B will be f of -4, 5 minus 2 times 4 squared, 5 minus 2 times 16, 5 minus 32, negative 27. Okay, now we need the formula. Okay, so we'll have minus 27 minus a minus 3 over 4 minus a minus 2. So it's minus 27 plus 3, 4 plus 2. So we'll have minus 24 over 6 minus 4. Okay, so now here we have A is negative 3, B is 3, f of A is f of negative 3. 3 times negative 3 cubed minus 1. Okay, so negative 3 cubed is negative 27. So we'll have minus 51. Minus 1 equals minus 52. F of B will be f of 3. 3 times 3 cubed minus 1. 3 times positive 27 minus 1. And that ends up being 50. All right, so once again, we apply this formula to find the average rate of change between A and B. So we'll have 50 minus 52. And then B minus A would be 3 minus minus 3. (102 over 9), which both of those are divisible by 3. Now, you don't always have to reduce everything to the smallest value. I mean, it's nice when you can do it. This is actually 34 thirds, but if you left it like this 102 over 9, that's fine. But this is the smallest we can get. Okay. All right, then. Those are straightforward. Now, oh boy. Yes. So these are straightforward. I mean, literally all you're doing is adding and subtracting them and dividing and multiplying. So these aren't so bad. These are the complicated ones, in my opinion, the composite functions. But let's see what we can do here. All right. So basically, I think the biggest thing we have to watch out for is the parentheses. It would be easy to make mistakes with negatives. So here, that shouldn't be a problem. Basically, what you're doing is looking for common terms, or sometimes we used to call it in math in high school like terms, meaning that they have the same exponent or else they are constants. These cancel each other out. So we just end up with 2x plus 6. And that's really all there is to it. Then for the subtraction, this is what I was saying about the subtraction. You've got to be very careful with the signs because you're taking the same setup, except now it's negative. And so when you drop the parentheses over here, it's minus 6 plus, oops, I wrote that wrong, sorry. That's better. Okay, so it's x squared plus 2x minus 6, but plus x squared. So we gather up the like terms, and we have 2x squared plus 2x minus 6. Okay, x squared plus 2x. This one is now you notice here we got a little bit lucky because we can do a simple FOIL on it. It doesn't always work out that way, does it? No. So f is these two. So here, it's a little bit more complicated than some of the other FOILs we've done. Here's O minus x to the fourth. Inner is these two. And then this is last, minus 2x cubed. Now it appears that none of these, there's no common terms, there's no like terms. So we'll just write this as negative x to the fourth minus 2x cubed plus 6x squared plus 12x. So notice the convention is to write them with the highest exponents first and work your way down to the lowest exponents and then save the constants if there are any for last. Now, as far as the division goes, sometimes you can simplify, but often you can't. So in a case like this, for example, I don't think there's any way to simplify this ratio, x squared plus 2x over 6 minus x squared. I think we're just going to leave it like this. I mean, you can do this, for example, but it doesn't really get you anywhere. I don't think so. Let's see. I'm going to do something on a piece of paper here. Actually, I might as well show you what I'm trying to do. Just in the off chance that x plus 2 is actually a factor of minus x squared plus 6. Here's what I'm going to do. Watch this. I'm going to first rewrite this as minus x squared plus 6. Oh, actually, no. I'm going to write it in a very unusual way. I'm going to engage in something which sometimes is called synthetic division, just to see if x plus 2 might be a factor of 6 minus x squared. So if I put an x here and multiply that by x plus 2, I'll have x squared plus 2x. Now, I'm going to subtract that entire expression. And by doing so, oh, no, sorry, I would need a negative here. This has to be negative. This has to be negative. I'll tell you why. Because I want to eliminate the x squared. So this becomes a positive term. When I subtract, this becomes positive. Oh, look what's going to happen. When I combine these drop out. This is 2x plus 6. So if I put a 3 here, what do you, oh, I'm sorry, not 3. Oh, no, sorry. No, it's not going to work, is it? Because this would have to be a 2. And then look what happens. Nope, not going to work. Sorry. So therefore, we'll just leave this the way it is. Because x plus 2 does not evenly divide into 6 minus x squared, there will be no simplification or cancellation. We'll do this again later on. I'll just quickly remind you, this is a technique you use when you try to divide one polynomial over another. We'll see a lot of that in chapter 3. So let me get it out of there for now because we don't need it. Not yet. All right, so we'll just leave it like this. That's kind of nice. Now these guys, the composite functions, we have to be super careful with these. Okay, yeah, we're good. All right, so for example, f of g of x. So here's what you do. You take your f of x and each x is replaced with g of x. Okay, so instead of 2x squared plus 1, we'll have 2 times g of x squared plus 1. That's the key to the whole thing. Whatever's in here, replace x with g of x. And then, of course, make the proper substitution. So in other words, that will leave us with, okay, now we can do FOIL on this one. Let's do this on the side here. Now, it may turn out that we can leave it like this, and maybe we should, but I just want to see what happens if we simplify it. You'll have (9x squared) minus 15x. That's, oh, inner is these two, minus 15x. And then this is last, positive 25. And so when you consolidate all those, it turns out that this equals 9x squared minus 30x plus 25. So that means over here, I can rewrite this as 2 times 9x squared minus 30x plus 25, all plus 1. So I'll have 18x squared minus 60x plus 50 plus 1. And then finally, I'll have 18x squared minus 60x plus 51. So I would say that, I mean, this would probably have been fine. But if you do simplify it, this is what you'll end up with. Now, I don't know if Symbolab can do this or not. I mean, it might be worth looking into it, but I've never, oh, here it is. Now look at this. Oh, our friend Symbolab. Let's see how it handles this. I'm going to, see, the problem is I'm not sure how it expects me to enter this information though. It's not always, it's not the most user-friendly software I've ever used in my life. You know, let me try this. I'm just dying to know if it can handle this. 2x squared plus 1. Oh, now why did it do that? And I think, but see, now the problem is I don't know how to enter g of x. It's not really letting me enter another function. So let me try this. Oh, this is very annoying because it's there. But they haven't exactly, I think that, I guess it's capable of doing something like this, but I do not see how to do it. If you want to fool around with this and let, you know, if anyone wants to really use this package and you discover something interesting, you can let us all know, because I like the potential that this software has, but, you know, like you can see what I mean. I don't know what this is supposed to do. It would be nice. Let me see what it says in the pre-calculus. No, I don't know. It looks like it's the same to me. Well, anyway, all right, so let's not worry about it right now. We're supposed to do it by hand anyway, so we can learn it. But I really was just wondering if it was possible to at least double check our results like this. Anyway, so let's get back to this. Now we have to work it backwards too for this next part, g of f of x. So in this case, let's just remind ourselves what these functions were. Okay, so this time the strategy is to take this and replace all x's with f of x. So g of f of x would be 3 times f of x minus 5, 3 times 2x squared plus 1 minus 5, 6x squared minus 2. That's it. Oh my God, that was too easy. And that's it. You're done. Now, the next two are easier because we're actually using constants. So for example, if you look at this one, f of g of 2. Now, what that tells me, is that your best bet is to solve for g of 2. Okay, so g of 2 would be 3 times 2 minus 5, which is 6 minus 5, which is 1. So now f of g of 2 simplifies to f of 1. Now look how easy that is. And now that simply means that you're taking this expression and you're replacing all the x's with 1s. All right, so if f of x equals 2x squared plus 1, f of 1 is simply 2 times 1 squared why is it doing this? Oh, there we go. Plus 1. So that's 2 plus 1, and that's equal to 3. So these are nicer. They're easier to work with because you're reducing one of them to a simple constant, and that makes things a lot simpler for us. Beautiful. Now here, of course, we have something similar. We're going to solve for f of 2 first. And so let me just quickly grab these again. And f of 2, therefore be 2 times 2 squared plus 1. That's 2 times 4 plus 1. And therefore that is equal to 9, or 8 plus 1, which is of course 9. And now g of f of 2 is equal to g of 9. And so since g of x is 3x minus 5, that indicates that g of 9 must be 3 times 9 minus 5, 27 minus 5, 22. And that's it. You're done. Oh, go ahead, Fernando.
I just want to ask if we want to refer back to all back to the notes for this class. Like I know you said that you put the recordings for class on YouTube. And
yeah, they're there.
Have
you seen them?
Math classes. Which one is ours?
Oh, okay. Hold on. Let's go to
I mean,
mine.
they're all. I see them there. I'm just asking because are they all our classes or different classes?
All right. So I created what are called playlists, and I was surprised at myself for being able to do this. So you go to our playlist, and this way, if you wanted to, I mean, you could look through all of my videos. I mean, there's a million of them. And that's why it's taking so long. And that would work. If you click one of these on, it'll start playing, but they're just all jumbled together. So in order to save you time in searching for what you're looking for, I would recommend very heavily that you go to the playlists, because that way it'll be so much easier. And there's others still here from the summer and possibly the spring. There used to be a lot more. I mean, I can't keep them all forever, but this one, oh, see, now these are the individual ones. Okay. But yeah, there it is. This is from September 1st, and it works. So yeah, just go to the playlist and that should take care of it. So oh God, let's get rid of this. So there they are. And when we're done today, of course, I'll put today's in here too. So every week, within a day or so, you'll see this new one posted here. This one takes a while to process. I mean, what it has to do is turn it into MP4 format, which is YouTube format. And for a 3+ hour class, that can take quite a while. So you might not see it until that evening, but yeah, it's there and you can download it. You can do whatever you want with it. It's, I don't know what else you can do with it besides watch it, but there it is. I suppose. Now, but what's interesting about this is that these are all publicly available. I did that on purpose because they're math videos. If somebody who isn't in this class wants to watch it, that's okay with me. And in fact, sometimes I notice that does actually happen. I guess somebody who searches YouTube for, how do you calculate the average rate of change between 2 points? This one might show up in their search list. And so, but anybody can watch this anytime they want. I don't know. Nobody's ever told me that they've ever had an issue with these. They work well. There's a lot of storage here, which is why it's here and not in Moodle, because I was told by the school not to put these in Moodle because they suck up so much space. But YouTube doesn't seem to have any problems with space. So you just put it here and anybody can have a YouTube channel. And so that's how this came about. And so again, I mean, I'm really not a tech person at all, not even close, but somehow I was able to do this. And you could do it too if you want to. If you have any ideas for videos, you just need a software that records your desktop and you're all set. Or you can use your camera or your iPhone and you can do all kinds of fun stuff. But here we're just doing math. We're serious people. We're just doing math. Okay. So there it is. Oh, and if you forget, if you get onto YouTube itself and you say, oh God, where's his channel? Just type my name. It should come up. There it is. Look at that. I've got 73 subscribers. Woohoo. Man, I must be zooming up there. Some of these people, if you've ever watched videos on YouTube, you get people who have literally tens of thousands of followers or even more than that. Apparently, when you reach a certain point, you can charge a lot of money for ads on your channel. And really, I guess that's one of the reasons why people make so many videos. But not here. We're above all that. We are just thinking about education only. So there's no, God, I hope there's no ads in my videos. I don't think they would just stick videos in there. I think only people who are trying to make money have videos in their YouTube videos. So the one thing that we were wondering about, and in one of my other classes, somebody raised this question about closed captioning, which I hadn't thought about. And apparently it can be done, but I don't really know how. So if you're interested in that, we might have to do some research. But as of right now, I don't believe they have closed captioning. But other than that, they're just like any other video on YouTube. They're, of course, very long. But as far as I can tell, the quality is pretty good. So you should have no trouble finding it. All right. Well, anyway, so Anyway, oh, here we are. Now, these are the tricky ones. These are the composite functions. So we have to remind ourselves what this notation actually means. Let's see. So in other words, what you're really doing is composing a function with itself. Okay. So in other words, that symbol, F, that little zero here, this actually is shorthand for, okay, f of x. Okay, so what you're doing is you replace all x's with f of x. Seems strange, but that's exactly what you're doing. But it's no stranger than saying square a square or take the square root of a square root or something like that. So f of x would be 2 f of x squared plus 1. And since f of x is itself 2x squared plus 1, what we can do now, although it may not be absolutely necessary, I would accept this as an answer, but if you feel like you want to expand it, you could apply FOIL here. Sometimes expanding it can make it simple, make it easier to simplify it, which is really the main motivation for doing that. But here this should be sufficient. But let's see what happens if I do FOIL. 4x to the fourth. Outer is 2x squared. Inner is also 2x squared. Last is 1. So I'll end up with 4x to the fourth, 4x squared plus 1. All right, and when you multiply that out, 8x to the fourth plus 8x squared plus 2 plus 1. So you finally would end up with 8x to the fourth plus 8x squared plus 3. Nice, okay. So it's really no different than the ones up here, f of g of x. It's just that now it's f of x, f of x. Now, what about this one? Well, based on the same logic, this one must be g of x. So you replace all x's with g of x. All right, so g of x is 3x minus 5. It must be the case that g of x is 3 times g of x minus 5, or 3 times 3x minus 5. Because remember, this is g of x. And then when you multiply it out, you get 9x minus 15 minus 5, 9x minus 20. All right. So that was it. Okay. Well, that was a long problem set, I must say, but we need the practice, don't we? Yes, we do. All right, so I'm going to save this right now, and I will post it, of course. In fact, why wait? I'll post it right now. I'm Moodle.
Hey, I got a question.
Go ahead.
Can I at least get the topics like we've been going through so far, like like what's this topic called? You know what I mean? That
this is called composite functions.
Oh, okay.
Okay, so in other words, if you wanted to look this up on the internet and say, listen, details, this section is called composite functions.
Okay, cool.
These are average rates of change. And this, you would look for finding the domain of a function. Okay, so yeah, if you, I'm sure there's a lot of math websites where they'll give you plenty more examples if you need them. And so, but you're right, you need to know what to look for.
Yeah. Wait, can you possibly list the topics we've been through actually? Like, I just want the name, you know what I mean? I don't
I
want you
mean,
to like
for
go through.
just today or for everything that we've done?
Yeah, the topics that we've been through for everything.
All right, I'll tell you what, let me get the slides open.
Thank you.
Sure. Now, sometimes it's not that simple, but we'll do what we can. Do you have a website in mind? Is there a website you've stumbled onto that can do
No,
this?
the thing is, the reason why I ask, because it's like sometimes like I would search for tutorials and I'm like, wait, what the hell am I searching for? You know what I mean?
I get
like,
it. Okay.
I don't even
Well,
know the name that
Actually, I'm glad you raised this question because I didn't think about that. I
no,
will
this
do.
happened so many times in my math classes, like,
Mhm.
and it's like teachers never like say, hey, this is a topic we're talking about. You know what I mean?
Okay. Here's what we'll do. Now, in some cases, it won't really be that. We just have to run with our instincts. But we'll do what we can. Let me add this here. As long as we're doing this, I don't want to let it go to waste. Let me just I will save this list. And in fact, what we could do is even do some searching right now and see what shows up on the internet. And if it finds what we're looking for, that means we must have done this correctly. So yeah, no, very good, good idea. Because yeah, I mean, there's lots of great math websites out there, like especially the manufacturers of software. Like there's a company called Wolfram that makes math software. But of course, yeah, here's something. Wolfram makes software that is it's like, imagine if Symbolab was really, really powerful. That would be what they do. It's called Mathematica, I believe. And in fact, I think you can get a free copy of it as a student. But because that's what they do, they have all this good stuff over here. Like you said, you have to know what to look for. And all right, so let's see, what have we done? So relations, all right, so some of these are pretty straightforward. So if you actually went to the internet and typed in relations versus functions, you should probably be able to find what you need. So let's see. Finding the domain of a function. Finding the range of a function. Okay. Functions. Well, functions, that's a very general topic. If you type that in, you're probably going to find 100,000 pages. So maybe don't look for that one, but, or actually, I'll tell you what, yes, if you're just specifically asking for definition of a function, then you probably should be okay. Okay, now, just trying to understand what a function is, evaluating functions, where you're just showing how to assign numerical values to functions. Solving functions, but here you might want to be more specific, solving linear functions and solving quadratic. We haven't gotten past that part yet. So in other words, if you do ask for this one, focus your attention on linear functions and quadratic functions, meaning that there's an x squared term. And so therefore there will be, oh, look, I did go over this x plus m, x plus n thing. Huh, I thought I was throwing something new your way. No, we did actually do this, didn't we? Okay, good. One-to-one, and so these are more specific topics. One-to-one functions, that's a very simple topic. You can, okay, horizontal line test, vertical line test. Okay, see, the good thing though is that even if you just type something relatively straightforward, they'll show you some more examples. Well, this was meant to be a brief introduction to these types of functions: constant functions, identity functions, absolute value functions. And again, what you want to know is what are they and what are their properties? What do they look like? We'll see these all again, by the way. This was just, it was almost like a preview for a movie. You see on TV, they show you some exciting highlights. And all right, let's just quickly finish this up. Square root function, and then the cube root function. So let's say you decided I've had enough. I need to know what a quadratic function is, and you went up here and said, okay. Ooh, see, there's a whole look at this. There's a whole, I should have known, a whole website about quadratic functions. Now, sometimes these are very densely written. They're very complicated. But sometimes you might find yourself with a nice set of examples. So Wikipedia. Now, Wikipedia, I'll tell you what, often Wikipedia is a good source of articles about math. And I mean, sometimes they get out of control, but if you just want a basic overview of something, you can start with these guys because they often have what you need. Like here's some nice discussions about parabolas, for example, and what is the vertex? We will be discussing all this, minimum and maximum points and how to find them. So here's the quadratic formula, our old friend, the quadratic formula, which we'll also be using. Look at that, the golden ratio. Oh my God, how cool is that? That's something that we'll discuss this at some other point, but it's a kind of a fun idea that that this ratio seems to pop up over and over again in a lot of areas, like even biology and physics and anatomy and all this and that. And it may have been used by famous artists like Leonardo da Vinci. But all right, anyway, so, and if this, for the stuff that's more advanced than we did, just skip over it. But you know what? There's this place called Khan Academy, which you may have heard of. It's all free. This guy, he just spends his whole life making videos. Okay, I don't think you have to pay for it. It's always been free. But what they have here, it's a guy lecturing, and so Khan Academy. Let's say you want to know the quadratic. You want to understand more about the quadratic formula. All right, here you go. So here's Mr. Khan, and he's going to teach you how to use. Oh, stop that. The quadratic formula. And, it's potentially very helpful. I don't know what this energy point crap is, but here it is. There we go. So this is how they're all are. He's writing, I don't know what exactly this thing is that he's writing on. It's obviously designed to show different colors. It's literally a blackboard. But if you go to Khan Academy, and it's not just math, he has everything. This has been going on for several years now. He's very famous, I guess, you could call it the internet community. Everybody knows about Khan Academy because he must have thousands of videos by now. So I would start here, not even with Wikipedia. I would start here if you can find what you're looking for. So when we're doing the quadratic formula, he's going to go through it with you step by step. God, what is this energy point crap? It's very annoying, but So you could click it on and watch it. And plus it has the closed caption if you want it. And then he'll just go work through a bunch of problems just like this, just like we do in class. So I would put that on top of my priority list. But anyway, so we went through all these functions just to take a peek at them. And also don't forget, if you need to visualize what a function looks like, don't forget about Symbolab. So we found domains and we found ranges. Okay, I'm sure Khan has something about that. Piecewise, this is just a special case. Rates of change. Okay, we did that.
Can you go up a little bit so I can screenshot
Oh.
this?
Yes. Okay. Where do you want me to stop?
Wait. Go go on top of relations.
Right here?
Yeah. I'm just trying to capture as much as I can.
Oh, okay. All right. No,
Okay,
I'm going to post this anyway on our.
Oh, okay.
Moodle. So
Sweet,
you don't have
thank
to
you.
take pictures of it. Yeah, as long as I'm typing it up, I might as well just. There's no point, in like I said, letting all this work go to waste. I'll just post this, and so you'll all have a copy of it. If you want to go to Khan Academy and search for these topics, and then if it's not there, you know, you can try it someplace else. But Khan Academy is like the gold standard of these instructional videos, and it's all for free. I guess I don't know how he makes money from it, but he's been doing this for quite a while now, and he's branched out into other areas too. Like I was starting to say, it's not just math. If you need help with economics or a lot of other topics, he's got it too. But yeah, rates of change, and oh yeah, we talked about maxima and minima. Okay, let's add that here.
I also
What
have
you're
another
doing-
question.
Oh yeah, go ahead.
So far we had I think chapter 1 and chapter 2 homework, and I was wondering, what was those homework based off of, what topic?
Oh, we did. So if you go back, the only one that we're done with completely is the first one. We did the first one last week, and here it is. Oh wait, sorry, that's the wrong one. There it is. So this was evaluating functions, and oh, I think that's all we did. Evaluating functions. Okay, so this one was exclusively based on evaluating functions.
And
So-
is like evaluating functions like mostly finding X or something, or like?
Well, what you're doing is you're replacing X with a specific value and solve
Gotcha.
it.
Okay. And that's
then-
the value you gave on top, right?
Yes, remember on top, it would say something like, what is f of a, or something like that. What is f of 3? All right, let's open it up again. So yes, what you're saying is f of -3 means take your function and replace all the x's with -3s. And that's what this is all about.
Can we? I don't know if it's too late. Can we do like number 1, for example?
All over again?
Yeah.
All right, well, here's the function f of x. So if it says to solve for f of 3, -3, you literally just first start by replacing all the x's with -3s. And once you've gotten to that point, the rest is just algebraically rearranging the equation.
Almost like
And-
PEMDAS.
PEMDAS, yeah. And then you see here that this actually ends up equaling -11. So literally
Gotcha.
all you did was replace the x with -3, and that gives you -11. So let's say this is a function that determines, it could be anything. It could be the profits, it could be, force that's being applied to something. But what matters is that whatever x is, you replace it with this constant, or in some cases a letter, and just algebraically solve for the function.
So basically most of this evaluating functions is just plugging in pretty much.
Pretty much,
Right,
exactly. Literally,
gotcha.
that's what it is.
Okay,
Plug it in
I
and
got
then
it now.
algebraically solve for the whatever it is you're looking for. Okay. So in other words, it's
Thank
not
you.
enough to plug. You've also
Thank
got
you.
to solve. Okay. Yes, that's every one of these is the same in that way. So once you go back
Gotcha.
and look at this, and make sure once you try to get the answers without looking at these answers, that to me that's the best way to do this. Just take the original question sheet that doesn't have the answers and try to do a few of them and see, and then every so often take a peek at the answers. And if you're getting them, you're fine. If not, at least here you've got all the steps. This is kind of like a black and white version of Khan Academy. I don't have that cool, colorful blackboard, but all the steps are here. But and then you know what? If you come along and say, "Oh, I don't understand what happened here," you can just ask in class next week, or you can send me an email.
Gotcha. I got it now. Thank you. I appreciate it.
Because you never know, like when something could have been explained a little more intensively, there you never know. It's hard to include everything. So yeah, this is what I would recommend. Go through these and just without looking, see if you can get the same numbers. And if you can't, just see what happened. Because most likely you're doing the same wrong thing over and over again until you get that straightened out. Once you do, you'll be all set. Let's put it that way. Okay. Oh, what website, Fernando, are you talking about? Khan Academy?
Yeah, Khan Academy is the website I usually use a lot more frequently. It helps, it's very diverse on many, many subjects. So
It does.
it's a really
It has,
great website. Just
yeah,
just playing it out. There's really good stuff. So it's really helpful.
because he started out with just math and then he branched out into these other fields, and I guess he's got a lot of time on his hands. I'm sure he's an academic, but he just decided, you know what, if only there were videos online that could help people, and there aren't any, therefore I will take care of it myself. Well, more power to him, because I can tell you how time consuming this stuff really is. It must really suck up all of his time to do this. But not only that, but let's see, what else? Oh, there's people down here writing in, so you might also see other people with other questions that are similar to yours. You never know. So this is really potentially insanely valuable. And now it says here there's a video. I don't know why you would need this. Can you imagine reading this instead of watching it? Look at this. But you never know. I mean, if for people who are either visually or they don't hear well, this might be the only option they have. But I would watch the video. So, all right. Anyway, so let me finish this list real fast. I think that might have been it. Composite functions. Oh, evaluating composite. All right, I'll add that as a separate topic. And what else? Finding, okay. I'll tell you what I'm going to do here. I'm going to turn those into sub headers. Because that's what they are. Okay. And so if you go to Khan Academy and say composite functions, please, I'm sure he has, decomposing, okay. And, we did talk, absolute, okay. This is pretty straightforward. It's just that all you have to do is recognize what exactly does an absolute value mean. So you're basically rewriting it in two different ways. And this is in one of our problem sets, by the way. The way it's written, just take this part and set that equal to 5 or 0, actually, in this case. And then you need the negative of that. And you do the same thing. Inverse, that's something. Okay, there we go. We did that a lot. And then ultimately finding domain and range of inverse functions. Oh, I think that is it for chapter 1. Okay. All right. Now, so this chapter 1 problem set number 2 is done. So I'm going to save it again. And I'll post it, of course. And then we had a third one. Okay, now the third one is all about, let me go find it. Oh, speak of the devil. Absolute value functions. Okay. Oh, actually, I've also formally typed up the answers here too, but I think it's better if I go through it with you rather than just posting this. So let's start with this first one. Now, here's what you're doing. There's 2 solutions here. So, you know what, let's go to Symbolab. I find that it's always very helpful if you can visualize what these functions are doing, because remember when you say solve, what you're really looking for is where does the function cross the horizontal axis? So look at the picture. By the way, if anybody stumbles onto a cool website that's very helpful, I hope you'll feel free to share it with the rest of us, because I'm sure there's plenty of others. And anytime you find a new one, that's a cause for celebration. That's for sure. All right. Oh, that's bizarre. Oh, you know why? Because I typed it wrong. I was going to say, oh my God. Oh, I know why. Because I wasn't supposed to use the Y. Okay, here we go. So in other words, you see how there's 2 points, 6, 0, negative 12, 0. The 2 x values, 6 and negative 12, are the solutions of this equation. That's what we're looking for. We know that y is equal to 0 by definition here. It's the x's that we're after. Now here it appears that they have actually done this for us. But let me show you what they've done. Now, I don't know if I like doing it this way. Let me show you what I think is the best way to do this. So you've got 2 solutions. One of them is just the x plus 3. Well, this one was easy. I just subtracted the 3. Now over here, I'll write this out as minus x minus 3 equals 9. I'll add 3 to both sides. Okay, so if you were trying to visualize this, that's what we're looking for. Now, if you're not sure, plug them in. Like if you plug 6 in here, you'll get 9, absolute value of 9 equals 9. But if you plug in negative 12, you'll get absolute value of negative 12 plus 3, which is actually negative 9. But remember, the absolute value of negative 9 is just 9. Okay. So that's all you have to do in these cases. All right, remember 6, 0, negative 12. And the right here, the peak, I suppose, the bottom line here is this negative 9. because you're basically trying to find out where this whole thing equals +9. Okay, now let's do the next one. So what I've done here, I've just got whatever was inside the brackets, 6x minus 5 equals 5. 6 minus x equals 5. Over here, I've multiplied the interior of this by -1, okay? Once you've got that part straight, the rest is just algebra. So I'll subtract 5 from both sides. Okay. And then I just end up with a 1 equals x. Over here, I have -6 plus x equals 5, x equals 11. So we can double check this with Symbolab. Absolute 6 minus x equals 5. Okay, 11, 0, 1, 0. Is that what we got? Yes, it is. Okay, so we have done it correctly, and it's nice to have a way of double checking. It's always nice to have that. So sometimes in the Symbolab, what you're doing with it is you're not using it to actually solve it, whatever it is, but double checking your results, which is always very helpful. Okay. So these are pretty straightforward. Once you've done 2 or 3 of these, you should never have trouble with it again. So here, once again, I'll just do 2 things. 5x minus 2 equals 11 and minus 5x minus 2 equals 11. By the way, I do want to point out one thing, though. When you're watching instructional videos, often there's more than one way of getting at the same answer. And sometimes what might happen is they may use a slightly different approach and still get the same answer. So we always have to be aware that there's almost without fail in math, multiple ways of getting to the same point. It's like, how many different ways are there to get from your house to school? Well, there's lots of them. So if you run into a video which is doing this differently, just be aware that whatever it is, it would be equivalent to what we're doing here. But, you know, so we want to avoid getting confused, but, you know, hopefully that you won't run into that too much, but it is possible. So anyway, so let's carry on with this. All right, now here, remember to distribute that negative sign. If you do this part incorrectly, there's no way you're going to get the right answer. So subtract the 2 and divide out the -5 from both sides. Okay. Now let's go double check our friend Symbolab. 5x minus 2 equals 11. (13/5) and (-9/5). What do you know? Also, I noticed that I think, once again, they're doing it in a slightly different way algebraically. But we're getting the same answer. That's what matters. Now, this one, oh, they had to challenge us, didn't they? This is what I recommend you do in a case like this. Simplify it to make sure that the left-hand side is just your absolute values. In other words, see what I did? I divided out the 2. Now you can carry on from there. So in other words, just algebraically rearrange it to make sure that all that you have on the left-hand side is your absolute value. Now this one, we have a problem. We've got 7/2. What I'd like to do is turn this into 8/2, which of course is the same thing as 4. And that'll make it easier for me to do what I have to do, which is subtract 7/2 from both sides. And I'm left with 1/2 minus x equals 0, or 1/2 equals x. On this side, I'll end up with the same problem. So let's turn this right away into minus 8/2. Now this time I'm adding 8/2 to both sides. Okay. Now, if you've started to get rusty with your algebraic skills, this is a good chance to start getting them back. So when you combine fractions with whole numbers like this, you've got to make sure you have a common denominator. And so, yes, Fernando, go ahead. Oh, no, something's going wrong with the sound. It's all garbled. You know what? If that's going to be a problem, I think you can type your question in the chat room, because right now the sound is a little rough. Okay, so is it something you can type? Okay, go ahead. Just type it in there, because no, I know you can't tell from your side, but the sound that we were hearing was very difficult to understand, which means that the net is slow. Good old net. The net is helpful and all, but I wouldn't bet my life on it. That's for sure. Anyway, in the meantime, or else try it again. See if maybe the reception is improved. Oh, how did you get rid of? Oh, okay. All right, let me go through this again. The absolute value lines. This is the part where you're basically so to speak, getting rid of the absolute value lines. In other words, if you had something like this, this is equivalent to saying that x equals 3 and negative x equals 3. Okay, then you solve. Now this one is already solved. And you can tell this must be true because the absolute value of 3 is 3, and the absolute value of negative 3 is also 3. So in this first row, I'm doing two things. I'm taking whatever's inside the absolute values, symbols, and just keeping it. In the second case, whatever's inside, I'm multiplying it by -1. Okay, so this is basically negative whatever's inside the absolute value signs. Now, as far as this goes, let me show you this separately. If I had a situation where I was told that x equals 4 plus 7/2, or actually I should say minus 7/2, I can't directly combine these because they do not have a common denominator. So what I need to do is rewrite them so that they do. So I can, this is, I have so many options here, but what I really need is halves. So what I'm basically doing here is multiplying 4 by 2/2. Now I'm allowed to do that because 2/2 is just 1. I can multiply any number by 1 without changing its value. Now, what did that accomplish? Oh, by the way, I just want to remind you too that 4 is the same as 4/1. And now when you multiply two ratios together or two fractions, you can multiply the numerators together and you multiply the denominators, and this is what you end up with. So this is what I was saying before. If your algebraic skills are getting a little rusty, first of all, you can always just say, listen, how did you do that? And they'll review it with you. But after we keep running into these, you'll get more practice and you'll say, oh, I remember how to do this. So you've definitely done this before, but maybe it's been a while. So whenever we try to combine a whole number with a fraction, we always want to take that whole number and find a common denominator. So since 4 equals 8 halves, that's a more convenient way of writing 4 than simply leaving it as 4. Okay, then I can combine it with -7 halves. Otherwise, what do I do? So yes, I need a common denominator. And in fact, if you want to look that up on Khan Academy, go look for finding common denominators. I'm sure he has a video that at least mentions this because it's an important skill. And if you've forgotten how to do this, it's going to hold you back in this class. So if you need more practice, you can go to Khan Academy and ask for finding common denominators. So in fact, while we're on the subject, let's do another one. Let's try this. X equals 3 plus 4/5. How would you handle that one? Oh, I need fifths. Am I changing anything by multiplying by 5/5? No, because 5/5 is 1. So this is equal to 15/5 plus 4/5, which is 19/5. Okay, so that is often a very useful technique to have. Yes, so the absolute value, oh good, okay. As far as the absolute value is concerned, remember, it means there are two things going. It's a very compact way of expressing that there's actually two things going on. So like I said, let's say you had something like this. This is the same, this is just shorthand for saying that both of these two things are true. Okay, we have the positive version. And the negative version. This is the x minus 2. This is the minus x minus 2. And they both cross the axis at a specific point. And over here we have minus x plus 2 equals 4. Minus x equals 2, x equals -2. And so that's what this is really telling me. It's saying, oh, we have a function such that the function crosses the axis twice. And here's how you identify them. Whatever this is just simply the negative of this. Okay. All right, I hope that makes sense now. So in fact, now here, like I did say, why don't we simplify this first? Get rid of this pesky 3. It's only going to make things more awkward. Now we can split this up. And so now, whoops, we have thirds. We need thirds over here. So let's take this 5 and multiply it by 3/3. And this gives me 15/3. Now, eventually x has to be on one side by itself and it has to be positive. So here's what I'll do. Subtract the 5/3 from both sides. Now I add the x to both sides. And that one's done. Over here, I apply the negative. Let's turn this 5 into thirds. This is minus 15 over 3. Now I'm going to add 15/3 to both sides. And voila. Okay. Now, that should be the last of the absolute values. But just for the fun of it, let's investigate it on Symbolab. So by the way I've rewritten it, we can leave it like this: 3, 5 minus x equals 5. That should take care of it. And we'll see on the graph, what do you know? 20/3, 10/3. Now this time they're both positive. That can happen, by the way, because this is where they cross the axis. These don't necessarily both have to be positive and negative. So that's this case. Okay. So they're all the same. Once you get the hang of it, you'll never have a problem with it again. Now, the inverses. Now, this is a big headache. Well, it can be a headache. So because it's already 10 of 10, I'll tell you what, why don't we knock it off for our morning break? When we get back, we'll dive into this. This is a fairly complex topic. So it makes sense to save this for after the break, I think. So we'll get back to this. And we're done with this. We'll be done with the homework problems and we can get into chapter 2 again, which will be fun. But you know what I'll do too? Let me go get my list of topics. Here it is. And what I'm going to do is the same thing as we go along. I'll try to remember to do the same thing in chapter 2 so that I can post these. You know, I would have done this before. It just never occurred to me that this could be useful. So I'll try to remember to do the topic lists as we get to the chapter, just in case you need it. In fact, let me save this right now. Okay. Okay. All right, that should do it. So when we get back, we'll do these inverses, and then when that's done, we will start chapter 2, and we'll go as far as we can. And then now, because we're not likely to be completely done with 2, that means there are no new practice problems you can realistically do for next week. So for this week, we'll just pay attention to covering the material, and I'll post the solutions to these chapter 1 problem sets. So you have all 3 of them and you can study them at your convenience. But there won't be anything new for next week. We'll just continue with 2 and then probably start 3 next week. Okay. All right. So see you all in a bit. Make sure that you are plenty stimulated when you get back because, you know, we're going to need it. Okay. All right. See you in a bit.
Titanic had a nice drink. It was about to sink. The head chef of Florida, Manning Charles Jowen, was literally in his room getting drunk. He had already downed a few drinks of whiskey, but still, when evacuation orders came, he immediately gathered his team and began to help out. He started supplying each lifeboat with bread and helping women and children get into it. And when some of the women actually wanted to stay on the Titanic because they thought it was safer, Charles literally just picked them up and threw them into the lifeboat. In the end, he was offered a spot on one of the lifeboats, but actually refused and let someone take his place. Then he just walked back to his room, chill as a cucumber, and started drinking more whiskey. As the ship became more and more submerged, all the other passengers were completely panicked, but Charles himself was absolutely fine. Eventually, Charles fell off the boat, and while most people didn't survive 30 minutes in the -2 degrees Celsius water, Charles somehow managed to swim in it for 2 entire hours. Charles eventually found a lifeboat and was rescued. Incredibly, Charles was more or less okay and literally went back to work in just a few days. Back when the Titanic hit, Slugger's a lot of jackets of a similar style, usually for under 150. For obvious reasons, they're all going to be baseball related. If you want a more basic flight jacket, Cooper's a good brand. If you search long enough, you can find some that have patches.
Uh, All right, so we have one more problem. Wait a minute, where are we? Here we go. So basically, there's different ways you could do this, but I think the quickest way is to, and I saw this a technique in another book, but what you might want to think about doing to come up with an inverse is, first of all, you can write this as y equals x plus 3. And so now what you're basically going to do is swap the x's and the y's. Okay, so in other words, turn this into x equals y plus 3, and then solve for y. Oops. This is essentially what you're doing. And then solve for y. Whatever y is your inverse. Okay, so like here, it's pretty straightforward because now you can see that I can subtract 3 from both sides. So therefore, what this means is that if f of x is x plus 3, f inverse of x is x minus 3. Now, how do you prove this? Now, it's easy to say that might be it, but I want to be able to demonstrate that this is true. Now, it doesn't say you have to do this, but at least once, let's do this, just to remind you how it works. So what you're essentially doing is making sure that these two composite functions, oh, by the way, this minus 1 means inverse. I just want to remind you. F inverse of 1, that little minus 1 is pronounced F inverse of x. So therefore, I need to be able to demonstrate that both of these composite functions are equal to x. That's how we prove that two functions are actually inverses of each other. So we'll start with the first one. So this one f of f inverse of x means replace all x's with f inverse of x. So in other words, since f of x is x plus 3, what we want to do is say, all right, well, if that's the case, then f of f inverse of x is f inverse of x plus 3. Now, we are claiming that this is equal to x minus 3. And so at least this one certainly works. And then for this one, f inverse of f of x, replace all x's with f of x. So remember, the inverse function up here was x minus 3. Whoops. So therefore, f inverse of f of x is f of x minus 3. And f of x, the original function was x plus 3. And that equals x, so we're good. So we not only found the inverse, but we proved it. Now, sometimes you can tell by looking at a graph that this is going to be the case. I don't know if Symbolab is capable of doing 2 at a time, though. It would be nice. I'd like to be able to show them on the same axes, but I don't know if it's capable of that. that I'll have to investigate. It would work beautifully. It would be very nice. Now, also, sometimes, let's see, I don't know if it's capable of doing inverses. It might be. Well, you know what? There's always the internet. Now, the one thing I notice about this, it doesn't seem to have its own built-in instructions. So here's what I'm going to do. It's possible that somebody else has tried to do this, how to find an inverse function on Symbol Lab. So, oh, well, what do you know? I didn't think about that. It has a function, a button here called inverse. I don't know where that was hiding. Oh, it was over here. I get it now. So in other words, we were supposed to look in this menu. All right, well, let's try it. So remember, originally we had x plus 3. And it's saying right here, well, the inverse is x minus 3. So we've done it correctly. And oh, here they're even giving us some of the steps. They're saying that if we rewrite f of x as x plus 3, y equals x plus 3, which we did, then the big step is, oh, wait a minute, that's not the right one. I'm going to get rid of this one. Here we go. Then the next step is to literally, as I said, replace x with y. And then solve for y. Wow, it's being very helpful this time. All right, so reverse the x's and y's, solve for y, and you're done. Now, I don't know if it's capable of graphing both of the two. I'm not so sure about that. Oh, wait a minute. Well, let's see. Maybe we can do it here. X plus 3. And, oh, here we go. Now, I don't know how you're supposed to tell that they're inverses just by looking at this graph, but at least we can see that it is capable of doing both. All right, well, that's good. So the trick is, if you don't see a function listed on top, look over here. Like, oh, here's one. Look at this domain. Ooh. Oh, I didn't even realize this was here. Look at this. We might have saved ourselves some time earlier. Let me just try a quick example. 1 over x minus 2. Now we know that we cannot substitute a 2 into this. Let's see how it reacts to that. Huh. Wow. And it even gave us the graph. So you can see why x equals 2 is an asymptote. Man, I'm developing a bigger respect for this, this website. So that means that when you do your domains, you can actually double check your work on Symbol Lab. I had no idea. In fact, before I was trying to find a composite function. That one I did not see in here. It may not have that. But you know what? Investigate. You should go through here when you're doing your problem sets and see if maybe it has something that can be helpful to you. Look at this. It even has simplify. Let me try simplify. Let's try x squared. Let me try something that's very obvious. X squared over x, which will reduce, of course, to x. There it is. And you know, like I said, sometimes it'll show you the steps, sometimes it doesn't. But you know, they're hoping that you'll pay for it. But yeah, but no, here they showed us everything. So look, this is great. So you should be able to take advantage of this on your assignments. God, what is this doing here? H2O. But anyway, all right, well, this is good to know. So let's go on to the next one. We'll follow the same procedure. So once again, we'll follow the same steps. Y equals 2 minus x, and we'll replace or reverse the x's and y's. So that means we'll have x equals 2 minus y, and then solve for y. So I'm going to add y to both sides. And now I can subtract that x. Oh, all right. These two. All right. These are inverses of each other. And once again, just because it's good practice, why don't we prove it? All right. And then we'll consult Symbolab and see how it reacts. So remember what we're trying to show. Show that both f of inverse equals x and f inverse of x equals x. Now remember, this is the original function. This is the inverse. All right, so let's do the first one. F of f inverse means replace all x's in f of x with f inverse of x. So the original function was y equals 2x. So now, oh, sorry, y equals 2 minus x. And that becomes y equals 2 minus f inverse of x. And since the inverse that we have come up with is minus x plus 2, we substitute, and then we'll have 2 plus x minus 2. Okay, we're good. Now we have to do the other half of this. F inverse of f of x means replace all x's in the inverse with f of x. Okay, so we're claiming that the inverse is minus x plus 2. So now this becomes y equals minus f of x plus 2. And f of x itself, the original function was in fact 2 minus x. So this is where we're going. And there we go. Okay, we don't have to do this every single time. I just want you to remember how this works. So let's focus now on just getting the correct answer. Now you can see once we start getting involved with radicals and roots and all the rest, it starts to get a little tricky, but it doesn't have to be a problem because, again, as usual, all we're doing is saying reverse the x's and y's, and then solve for y. So this becomes x equals y squared minus 5. X plus 5 is y squared. And therefore, the square root of x plus 5 is y. Or you can think of that as f inverse of x. All right, now why don't we demonstrate that with Symbolab? Okay. The inverse of x squared minus 5, according to Symbolab, is oh, you know what? I just remembered. Sorry, I should have put plus and minus symbols here. Because when you take the square root of a value, let's say you're taking the square root, you're told that y squared equals 16. The reason why we need two of these is because both of these work. In other words, 4 squared equals 16, but so does minus 4. So that means that in this case, there are actually two inverses, which is very unusual, but it's because there's a square involved. It's radical x plus 5 and negative radical x plus 5. Because if you plug them into the original function, you'll see that you'll get the result that you're looking for. Interesting, okay? So don't be shocked when you see something like this. When you take the square root of a value, there's technically two solutions, one positive and one negative, because both of them work. And we can apply the test to both of them. We're not going to do that here. We know how that works now. All right. Now let's look at this one. Y equals radical x plus 3. And once again, reverse x's and y's. Solve for y. All right, so we have x equals radical y plus 3. X minus 3 is radical y. So now we square both sides. And this is our final result. This one doesn't need two different signs, because when you square anything, it becomes positive. Okay, so here we don't have to worry about plus and minus. All right, let's see what Symbolab has to say about this. Radical x plus 3. Okay. Okay, so they wrote it as x squared minus 6x plus 9, which of course is the same thing, because if I apply FOIL to this, f is x squared, outer is minus 3x, inner minus 3x, last is 9. So f inverse of x could also be written as x squared minus 6x plus 9. And that's what they've done. There it is. Perfect. Oh, and again, they are, for some reason, they're being very generous with their steps this time. I wonder how much it actually costs to open this thing up and really have everything. I'm going to check it out right now. Oh, for God's sakes, $30 a year. Well, I'm not suggesting that you pay that. Although if you wanted to, according to this, you could pay $4.99 a month. I use this all the time. Maybe I'll set this up so that next time we meet, yeah, I think it might be helpful if you want your own copy. So I'll tell you what, I will investigate this. And at the very least, every time it says show steps with a little lock, that means that we would be able to, yeah, see what I mean? Oh, okay. So you can actually join it without paying any money, but yeah, what we need. Yeah. Okay. So I will investigate this when we're done. And at the very least, I can show you on the screen. Now, the only problem is, now I guess once I buy this license, I'm allowed to do this. See, the thing is, you've got to watch it with recording videos. You don't want to be recording something which is intellectual property that belongs to somebody else. But if I pay for the subscription, I think I could show this to you on my videos without getting into trouble. So we'll look into that because I think there would be cases where having this information could be very, very useful. All right. And also, if you look down here, sometimes if you were wondering, if you wanted to then go ahead and investigate the domain and the range, it's all down here. Asymptotes, you name it, it's here. Inflection points, we don't know what that is yet, but extreme points we'll investigate. All right, anyway, I do have access to, at one of my schools, they have a subscription to Mathematica, and I could use that. The problem is then you would need to have your own copy of it. And I don't know if that could work. So we'll stick with the Symbol Lab. Okay, now, here's I think this is the last one. So we'll write it as usual, y equals x over x plus 2. Reverse the 2, solve for y. This one might be a bit of a mess. So let's, yeah. Now, let's see what we can do. Let's cross multiply. xy plus 2x equals y. Well, it won't be that bad. So then what I'd like to do is get all the y's on the same side. So I subtract xy. Now I'm going to factor out that y, divide both sides by 1 minus x. And that should do it. Okay, so again, we'll confirm that with Symbol Lab. The function in question is x over x plus 2. And we wind up with negative 2x. Oh, you see what they did. And this is another reason why you have to be so careful when you look at other sources. I don't know how or why this happened, but what they've done is they've factored out a negative for some bizarre reason. So in other words, these negatives cancel each other out, but what they've chosen to do is write it like this, it looks like. No, they've got a negative there. Now, what happened? Maybe I made a sign error somewhere along the way. Hold on. X equals y over y plus 2. Okay, here we go. Well, that's just plain weird. Man, I don't know. I think something's not right here. X equals y over y plus 2. X equals y. Oh, all right, well, let's try this. Oh, I think I know what they did. Okay, no, I misunderstood. I believe what they did was this. Instead of writing it like this, they have 2x. Now, here I can actually factor out this negative sign. These mean the same thing because you can see when I apply the negative, it becomes minus x plus 1. So what they did was then they wrote it like this. So it is the same thing. It's hard, it's hard to believe, but it's true. I don't know why they ended up with this result, but this is the Symbolab version, but it is the same thing. So if you try to use Symbolab and you get a number that doesn't look right, it's possible that they've simply rearranged it algebraically, which they did here. So we do have the same answer. All right, I think that's it for this third problem set. Wow, that was a lot of material, but now we can go on and do something new. One more thing. This is the thing that drives me crazy with Word. You have to ask for page numbers, which to me is absolutely ridiculous. You would think that most people would want page numbers unless they say otherwise, but they see it differently at Microsoft. They have a very unique worldview, let's put it that way. All right, finally, we're ready for linear functions. Now, these are functions that happen to have that one key property. They can be expressed as a straight line. In fact, that's where this word comes from, linear. It's a line, and it's composed of two parts. M is the slope, B is the vertical intercept. In other words, that's where it crosses the the y-axis. And there's two different ways of writing the equation of a straight line. This one, which we know very well, is often called the slope-intercept form because it contains both in the expression. It has the slope, it has the intercept. You don't have to guess. Now, the slope, as you recall, is the ratio of the change in y to the change in x, sometimes known as the rise over the run. Because you're looking at the change between two different points. And think of this point as x1 comma y1. And here's the point x2 comma y2. So you're basically trying to figure out the difference in the y's divided by the difference in the x's. And the reason why it's called rise is because you're moving in this direction with the y's, and the run is this direction. So it's a nice, easy way to remember what this is all about. Rise, run. But formally, it is the change in y with respect to the change in x. Once you know the slope, you can algebraically determine the intercept. So here, for example, we have y equals x minus 7, which is clearly a straight line. And so those are the 2 points. I arbitrarily chose those 2 points. Now, by the way, it doesn't matter which is point 1 and which is point 2. You'll always get the same results either way. Okay, so don't worry about that, but you have to be consistent. If this is point 1 up here, for example, it has to be true for both x and y. If this is point 2, it has to be the same for x and y. So let's say that's the case. So how would you calculate the slope? So again, y2 minus y1, x2 minus x1. And so y2 is this one. This is y1. x2 is here. And here's the x1. So we've got minus 1 over minus 1. Ah, what do you know? It turned out to be 1. Okay. Now, you could tell already with this function, the coefficient of x is the slope. So in other words, there's an implicit 1 here. So x is the same as 1 times x. And since y equals mx plus b, in this case, y equals x minus 7, it must be the case that m equals 1, which also implies that b is -7. All right, so you've seen that before. Now, by the way, you can tell which direction the line is going by looking at the sign of the slope. If m is positive, that means the function is increasing. We have something like this. If m is negative, the function is decreasing. If m is exactly equal to 0, we simply have a flat line. It could be anywhere. Okay. Now, for example, the function y equals 3x minus 2. What do we know about this function? Well, right away we know the slope is 3. The intercept is -2. And because the m is positive, before we even look at the graph, we know that it looks something like this. Now, on the other hand, I just realized I didn't draw this well because the vertical intercept is negative. It has to be down here somewhere. All right, so in the next slide, I have the Excel function, the Excel graph for the function. And so, yeah, I mean, it's hard to see it from here, but this is -2. So this point is actually 0, -2, because x is 0 and y is -2. And then the slope, what that means is that if I increase x, let's say in this case by 2, delta y would have to be 6. The ratio is 3 to 1. Okay. So that's what this is telling me. Every time x goes up in this, the way I drew it, if x goes up by 2, y goes up by 6. But in general, we think of this as if x increases by 1, if x increases by 1, y increases by 3, and vice versa. Of course, they can decrease. So if x decreases by 1, then y would also decrease, but by 3. Okay, that's what it means. Well, that's what the slope means. And that never changes. By the way, it doesn't matter which 2 points you choose, you'll always get the same results. So in other words, the fact that this is a straight line results from the fact that it is a constant slope. Now let's look at -4x plus 5. Okay, same thing. Here's the intercept. Here's the slope. Slope is -4. So now x and y go in opposite directions. So if x is 1, y would be -4. If x is -1, y is +4. And that's how you can tell because of it's going down to the right. So x increases and y decreases. And that's what it means to have a negative slope. 2 things that are going in opposite directions, like the amount of time that you spend watching TV and your GPA, for example, could be an example of how these 2 variables go in opposite directions. Now, here's a very bizarre case. The way it's written, there's no x. That's because m is 0. Okay, so in other words, the fact that y is equal to a constant simply means the slope is 0. No matter what x is, y will always equal 1. It's an unusual function, but I mean, you know, because it's a constant. Whatever this thing is, it's a constant. Like the speed of light is a constant. So therefore, it's just always a single number. To plot this on the graph, you just have a flat line. Now, why is it flat, by the way? Because no matter what 2 points I pick, let's say I pick 2, 1 and -2, 1. If you notice, let's call this x1 and y1, y1. Oh, did somebody raise their hand? I missed it. It went by so fast I couldn't see it. Well, all right. Anyway, if you think of a question, go ahead. Oh, I hate to tell you, but we can't hear what you're saying. So could you type it in the chat room? Yeah, there's something about the internet that's it's making your sound very garbled. It's like my cell phone. Whenever I use it in my apartment, that's pretty much what it happens sooner or later. It's like a dead zone here for cell phone reception. I might as well be living in the middle of Nebraska. I mean, it's just so bad. But anyway, what I wanted you to see is that no matter where we are, the y's are always the same. So delta y is always 0. And this is why the slope is 0. Okay, that's the logic behind it. There we go. Here's the question. Oh, do I also sound gargled? Oh, damn it. Is that right? Is it sounding bad? Yeah, the net,
You're
like
good.
the net is, like I said, it's not as reliable as you think. In fact, during this whole COVID thing, I've discovered that emails are not quite as reliable as we seem to think either. They don't always go where they're supposed to go. Oh, okay. So maybe it depends on the individual. All right, that's good. I don't want to, if there's something wrong with my sound, we have to fix it. But anyway, yes, so that's why this has a slope of 0. The y's never change. That's the whole point. So it's a flat line, and it doesn't matter what x is. So in other words, what it's saying is that y does not depend on x. All right, now I did say there's another alternative way of writing these equations. Now you might say, why would we bother with this? Why not just stick with our intercept slope form? Well, sometimes this might be more convenient. Depends on what we're trying to accomplish. But what this is saying to us, before we were identifying the line with 2 points. Okay, we use the 2 points to find the slope and the intercept. This is saying to us that we can also uniquely identify a straight line if we know the slope and one of the points. Okay, so let me just add this in here somewhere. We can uniquely identify a linear function with 2 points or 1 point and the slope. Okay, either way, we'll end up with the same thing. All right, let's just throw that in there. Now, for example, if I take this expression, the point slope form, and rearrange it, you can see the slope makes sense. It's y minus y1, x minus x1. So let me show you how that would work. First, let's look, this is the abstract, the general form. We want to look at a specific case. And you'll say, it's kind of the same thing. All right, so let's say that our example is this. So we've got not what we're used to seeing. Y minus 4 equals 2x minus 5. So this is implicitly y1, and this is x1, which means the point that we know is -5, comma, -4. And the slope, as you can plainly see, is 2. So with that in mind, we can take this information and rearrange our equation to find the exact expression for the straight line. And when we're done, it will be in the traditional slope-intercept form. So here we go. Why don't we just do some algebra? So we add 4 to both sides. Distribute the 2 over the x minus 5 to get 2x minus 10 plus 4. Consolidate these two constants, and what do you know? So what this means is that y minus 4 and both mean the same thing. This is point slope form. And this is intercept slope form. They both represent the same thing. And if you picked a point at random, now here, remember, we claimed that the first one is telling us that the point -5 minus 4 is a point on the line. What we can do is demonstrate that by plugging that into 2x minus 6. So in other words, oh, wait a minute. I just realized it's not. All right, hold on. Let me just repeat the, it's y minus y1 equals m x minus x1. So you know what that means. The point is actually 5, 4, because these are supposed to be negatives. In other words, you see how this is y1 and this is x1. So because it's the way it's written, this is supposed to be subtracted. So the point is actually +5, +4. That's better. So 4 equals 10 minus 6, 4 equals 4. So we just proved it. The point 5, 4 is on this line. Okay. So here's one. Ooh, now here's some challenging. Well, let's do this. I'll tell you what I'll do. Let me rewrite these. We know y equals mx plus b. Okay, we know that one by heart. We've known that for a long time. It's one of those things you never forget. This one, yeah, I don't know. It just doesn't stick in our memories as well. It just doesn't. That's why it's, if there was a popularity contest, let's say for linear equations, the first one would win. Okay, so here's what I'd like you to do. Given this information, the slope is 3. The point is 6, -1. What I'd like you to do is first write the equation. And this is just for practice in point slope form. And then write the equation in the traditional slope-intercept form. Based on what you're seeing on the top there. Okay, this is, of course, slope-intercept form. Do that first, and then algebraically rewrite it to turn it into the traditional, I call it, slope. Oh, wait, I'm sorry, I wrote this backwards. My fault. This second one is the point slope. My fault. Hold on. Point slope form. And then up here we have the slope intercept form. Okay. Very good. So why don't you take a couple of minutes and do them both, and we'll see how you did. All right. So let's see how you did. So point slope form. Remember, m is 3, and the point you were given is y equals 1, -1, and 6. And so that means you have y plus 1 equals 3 times x minus 6. Now, that is the correct point slope form. How do we turn it into the slope intercept form? That's where the algebra comes in. Okay, so we start here. And now it really is just a question of rewriting it so that y is on the left-hand side of the equation and just y. And so let's see how you did. Y plus 1 equals 3x minus 6. The trickiest part would be evaluating this. 3x is first. Then we have minus 18. Subtract that 1 from both sides. And this is your result. So these both mean the same thing. But I think you'll agree that this is the one that makes it's easiest intuitively to understand it. All right. Perfect. Oh, somebody got the right answer. No, oops, almost. No, I think you have a sign error. Yes. If the constant is wrong, you must have had a sign problem. Okay, so now what about if we have just 2 points? What do we do? Now, we've already seen a couple of examples. So let's just say this is x1, y1, x2, and y2. So basically what you're going to do is first solve for the slope. And then number 2, substitute the slope and 1 point into the equation y minus y1 equals m x minus x2. All right, so let me show you how that works. So for example here, so remember the points are 0, 1, and 3, 2. So that means that delta y is the difference between y2 and y1. The denominator is x2 minus x1. So we've got 1/3 is our slope. So now we know that y equals 1/3 x plus b. And we can pick either point to plug into this equation. I think I wrote the wrong thing here. We're going to plug this into the other form, y equals mx plus b. Okay, so let's do it. Now, it doesn't matter which point you pick. So in the slides, I've chosen the point 0, 1. Okay. Oh, I was right the first time. What am I doing here? Oh, sorry. I had it the first time. You're plugging it into the point slope form. Okay, let's try that again. Y minus y1 equals mx minus x1. Okay. And now it's just a question of you make the substitutions. Okay, so here's your y1, and here's your x1, and here's your slope. Now it's just algebra. Okay, so in other words, if you took this, first of all, x minus 0 is just x. Now we add 1 to both sides, and you're good. So that is your slope intercept form. And you're done. All right, after all that work, you've got something. Now, we're going to see an actual real-world application here, which you might find interesting, especially if you've ever had a class in economics. This is straight-ahead economics. We're going to look at a cost function. In other words, how much does it cost to produce a product? Okay, so this is a nice little detour into an applied field. Economics is very mathematical, and so all of this stuff applies directly into economics. So let's say, for example, we have a company that makes a product. Now, the costs of production typically are assumed to fall into one of two categories. The fixed costs are the ones you have to pay no matter how much output you produce. Okay, oh, that's explained here. All right, fixed costs are the ones that must be paid no matter how much is being produced. Like, for example, rent, property taxes, salaries. The salaries of your employees do not depend on how many units they produce. They get paid X dollars and that's it. The rent, the landlord does not care how much you produce. You get to pay X dollars a month. End of story. The local government doesn't care. You pay X dollars in property taxes. So we call those fixed costs. The variable costs are the ones that are directly associated with the product itself. For example, if you're Starbucks, your variable costs would include things like the coffee beans, the milk, the sugar, cinnamon, because as we sell more coffee, these costs increase, of course. And if you don't sell any coffee, you don't have to pay for any of this stuff, or you're not using it up, let's say. So that's why they're called variable, because they change. They change with the amount of output that we're producing. So in this fictional case, we're assuming that this company has $1,000 a month in fixed expenses or costs, but every unit of their product costs them another $10 to make. Okay, so we should be able to use this information to figure out the total cost of making any number of units of the product. If we make no units, we'll pay $1,000 in fixed costs. But for every extra unit we make, that adds $10 to our total costs. All right, now, that's why we're writing it like this. Now, X represents the total number of outputs, number of units produced. And you can see the point of all this is that it's a straight line. Y is the total cost. So this is a classic example of a linear equation. $1,000, you can think of that as the intercept. $100 is the slope. So there's the intercept, there's the slope. This is what we're looking at. Well, now, here's the question. How much does it cost us to make 20 units of this product? Well, in a case like that, remember, Y equals 100x plus 1,000. Now, what I could do is rewrite this as f of x. And then the x is 20. So f of 20 is 100 times 20 plus 1,000. And that turns out to be 2,000 plus 3,000, 1,000, which is $3,000. So that's how much it's costing me to make 20 units of this product. I don't know, I thought you'd find that interesting. There's a lot of examples we can find for linear equations because they're everywhere. That's one of the more common types of functions we'll see in the real world. Now, graphing. How do you graph these things? By hand, I mean. Let's say we don't have Symbolab. What you can do is this. Pick any two values of x, and we'll evaluate them for each x. In other words, we'll plug them into the function and figure out the values of y. That will generate for us two pairs, or they're called coordinate pairs sometimes, but the pairs that represent 2 points in a line is what we're really looking for. X1, Y1, and X2, Y2. And so we can pick any 2 points that we choose. Okay, so once we know what they are, in other words, we're choosing the x's, the function determines the values of the y's. And then, well, we can draw them. So, all right, let me show you how this works. Here's your function. Now, clearly, the slope is negative 2/3. And the intercept is 5. So let's just say that we arbitrarily choose the points or the values of x1. X1 is 0. X2 is 3. So what would be the corresponding values of y? So f of x1 is 5 because I'm just replacing x with 0. F of x2, on the other hand, would be negative 2/3 times 3 plus 5, which is 3. So what I've just done is proven that the points 0, 5 and 3, 3 are on the line. And now we know from our understanding of the point, the slope intercept form, we can, well, I mean, we already have it here, but we can actually now just go grab 2 points. And when combined with the intercept, we should have no trouble drawing this thing. All right, so, I did it in Excel. It's a little clumsy looking, but you can see the intercept is correct. And the 2 points are on the line. And so this is what y equals -2/3 x plus 5 looks like, or at least you can think of it as a sketch. All right, if you're doing this by hand, you can think of this as a sketch, but if you threw this into Symbolab, you'd see that this is exactly what it looks like. All right, so this is all probably very familiar to you. I'm sure you've done this before. It's just that you probably could use a little practice. Now, here's an interesting application. Sometimes it's important to know not the vertical intercept, but what we will call the horizontal intercept. In other words, we might want to know where the function has an a y value of 0. That would be defined, this point, as the horizontal intercept, or sometimes you can think of it as the x-intercept. You don't see it used as often. Usually we think about the y. This is the y-intercept, or sometimes it's called the vertical intercept. And this is staring you in the face when you look at the equation of a straight line. So that's the easy one. What about the horizontal? What if I do need to know what's the value of x when y equals 0? Well, it's not that difficult algebraically to do this. So what I'm going to do basically is start with my original function, and then, because remember, this represents y, I'm going to set this equal to 0 and now solve for x. Okay, so, I mean, you can see from the graph, it's approximately, let's say 7.5 maybe. But let's see the exact value. So I set these equal to 0. Now, oh, by the way, here's a little algebraic review. I don't want 2/3 x, I want x. How do I get rid of the 2/3? Oh, I have an idea. Let's multiply both sides by 3/2. Now, can I do this? Yes. I can multiply both sides of any equation by any number that I choose and not affect the results. Why did I pick 3/2? Because the 3/2 and the 2/3 will give me 6/6, which is just 1. So I've got x equals 15/2 or 7.5. Okay, so in other words, the graph actually is showing us what we need to know, that when y equals 0, x equals 7.5, that is what we mean by the horizontal intercept, 7.5. Okay, so in case you need that information, this is how it's done. All right, now here's some more interesting cases. Whoops. Horizontal and vertical lines. Any linear function can have a positive or negative slope. Now, here's where it gets interesting. We've already seen that if the straight line is flat, the slope is 0 because y never changes. Remember, the slope is delta y over delta x. With a flat line or horizontal line, since y never changes, delta y equals 0. But what about the vertical line? That's a very challenging case. What do I mean by that? Let's take a look at a vertical line. Let's say we had something like this. The equation of a vertical line will be something like x equals 3. X equals a constant. You notice it does not ever actually cross the y-axis. That's why the b is missing. But what about the slope? Well, remember the slope is delta y over delta x. So let me just randomly pick 2 points here. If I wanted to calculate the slope of this function, watch what happens. Remember, this is x1, y1, x2, y2. What happens when I subtract y2 from y1? Not a problem, but look at this. Oh no, I have division by 0. So what we'll do here is say that the slope of a vertical line is undefined. Okay, undefined, because it would lead to division by 0. So a vertical line, for a vertical line, the slope is undefined. The horizontal line is fine, it's just 0. But here, the slope is undefined. But I'm hoping you can see why, because the delta x will always be 0, and that will lead us to the one thing we must never do, and that is, of course, divide by 0. And by the way, one more interesting feature here, that implies that this is a relation, but not a function. Why? Because remember how that works. If these are the x's, this is being associated with more than one value of y, and therefore it is not a function. So it's not even a function. It not only has no slope, but it doesn't even qualify as a function. And in fact, you might remember the vertical line test tells us whether or not we have a function. The vertical line test fails. Okay, so this is not a function. It's simply a relation. It's a set of ordered pairs like 3, 0, 3, 1, 3, 2, et cetera, et cetera. Okay, but that's an unusual case. You don't see that very often. All right, now here's a fun topic because you've done this before and it's really, really simple. I'm gonna remind you of 2 words that you've seen before, but maybe you've started to forget what they mean. Okay, let me start by asking you a review question. What does it mean when 2 lines are parallel? Parallel, remember that word, parallel? What does it mean? All right, let me show you a quick graph of that.
Wait, I can tell you what parallel means.
Okay, what does it mean?
When 2 lines are going to the same direction.
Okay, but there's more to it than that. They have to have the same slope. Okay, so if we have y equals, let's say 3x plus 2 and y equals 3x plus 1, these lines have the same slope, but clearly not the same intercept, of course. And that's all it takes to conclude that they are parallel. And guess what? Unlike every other line out there, they never intersect, do they? No, they do not. They go on forever. They never touch, they never cross. They're parallel. Ooh, so the way we can identify them is by showing that they both have the same slope. And in terms of geometry, you can see they never cross. Okay, now The other term, though, perpendicular, who remembers what that means? Perpendicular. You learned this word at one point in your lifetime. It's starting to come back to you, and these memories are flooding back now, aren't they? Somewhere in your memories, all of this wonderful math knowledge is stored away in one closet somewhere, which you haven't opened in a while. Now you open the door and pow, all of this stuff comes flooding out. So perpendicular means what again? Okay, let's say you have this. I'll do a simple case. This is a flat line. What happens when they cross? Remember this little symbol used? What does this represent? That is used to indicate that this is a right angle. Oh, God. All right, here we go. This is a right angle. What does that mean? How many degrees are there in a right angle? Oh, we're digging deep now. 90, yes, exactly. I'm glad you all still remember that. But this is what perpendicular means. Where the lines cross, it forms a 90-degree angle. All right, so therefore these two lines that I've drawn for you are perpendicular. They cross at a right angle. Now, there's a formal way of proving this, though. Here, it's just enough to note that they have the same slope. How would you prove that two lines are perpendicular? Well, it turns out that if the product, and I'll show you an example of this in a second, of their slopes is -1, they can have different intercepts, and they will, but as long as the product of their slopes is -1, they are perpendicular. So for example, y equals -2x plus 1, and y equals 1/2, let's say, plus 4, -2 times +1/2 gives me -1/2, which implies that these lines are perpendicular. So let's see what that looks like in Symbolab. Now I think I remember how to do two lines at a time, but oh boy. Okay. It's something to do with the graphing. Remember before we found it by accident? All right, I guess it's time to visit Google. All right, my computer is being a pain. Hold on one second. It gets like this every so often. Like I said, you should never completely rely on technology. Like you can have all the map quests and all the other stuff you want, but you might want to just look at a map and write down the steps at some point. Oh, well, that's interesting. See, now it went there, but I would not be able to do that again. I actually stumbled onto something called graphing calculator. Yeah, that's the one thing I don't like about Symbolab. It's really not always that user friendly. But all right, let's see. What example did I have? No, not that one. Here it is. Here it is. Negative 2x plus 1. And 1/2 x plus 4. So yeah, I mean, if you zoom in on this, you can see, even though they're tilted, that's still a right angle, isn't it? Yes. Okay. So if you took out your protractor, you could show that this is 90 degrees. Okay. Remember the protractor you had in whatever grade that was? Anyway, so now what happened? It just disappeared on me. But you saw it, didn't you? I don't know what's going on with this thing, but yes. Let me just see something here. Graphing calculator. I just want to go back to Symbolab and see how I can bring that up without looking for it every time. Oh, it was up here. Okay. All right. No, wait a minute. This is not what we had before, is it? Oh, no wonder, because God, no wonder this is negative. Sorry. That's it. So while it lasts, before it gets erased, you can see that this is a right angle. So these are definitely perpendicular to each other. You can shrink it out too if you want to. But yeah, that's how we can tell. So while we're at it, let's do a couple of parallel lines. You can see, yes, the distance between them is a constant. They will never cross, okay? All right, so that's what we mean by parallel and perpendicular. Here's another example of two parallel lines. You can tell because they have the same slope but a different intercept, which I did in Excel. And you can see these two clearly are perpendicular because 2 times -1/2, as we've already seen, is -1. And this is the graph. Now, this is why I'm hesitant to use Excel. You can see the graphing is a little thin, let's say, for math. It works fine for a lot of things, but I wouldn't really use it for math. It just isn't really that sophisticated. But if you need something really high powered, that's when packages like Mathematica start to pay for themselves. So let's just say you've decided that, you know what, math is your thing. And you can see now, that's definitely a right angle. Yeah, what if you decide, you know, math is my specialty. I love math. It's my baby, okay? At some point, you will need something more advanced than Symbolab even. And so that's why I was mentioning before this Mathematica. A lot of colleges, as you know, do have free software for the students, which will be free as long as you're at the school, of course. And it's possible that Purchase has Mathematica. I'm not saying that they do. I don't know that for sure, but some schools do. And if you're really heading down this path, you might want to get your hands on it sooner rather than later and play around with it. It's like basically Symbolab raised to the 10th power. Okay, so it's very sophisticated, but it can do so much. Okay, so you know, it's something to think about. I'm sure, well, I'm hoping at least some of you are math majors, or at least math and computer science majors, because you know, that's a very good field to be in. And if you have those skills, you're going to be well paid for them one of these days. Okay. Oh, how about this? How do we know where the intersection point is between them? How do we know where they cross? Good question. Like here we saw, what is that point? How do we know? Let's find out. What you're going to do is set them equal to each other. Okay, not the y part, just this part. And you're going to solve for x. And here you can see, after doing a little algebra, we end up with 17/5 for x. So what do we do about y? Well, that's easy. You plug this x back into either one of these two equations, and you'll get your y, which turned out to be 6/5. So in other words, the point of intersection is this x and this y, 6/5. And if you're not sure, you can plug these into both equations and you'll see that it works. Okay, in other words, if you substitute 17/5 into either of these two equations, they'll both give you an answer of 6/5. And that's how you know you did this correctly. Okay, so that's pretty simple. Now, let's do a quick example of this with the real world, okay? So we have a sporting goods company that sells football helmets. In order to produce the helmets, they have a fixed cost of $250,000 a year. And on top of that, the helmet has a variable cost of $120. We can sell them though for $140. So now there's going to come a point where the cost of production will exactly match the revenues from selling the helmets. That is known as the break-even point. Okay, at what level of output do we have the same revenues and costs? That we call in economics break even, which means that you're making no money. Okay, so let's find out what that point is. So we're going to set up an equation for both. So the cost function, remember we talked about this earlier, the variable cost is $120 per unit. So that's 120x. The fixed cost is a constant, which is 250,000. Okay, that's the cost function. Now, what about the revenues? All we know is that each helmet that we sell brings in $140. So what kind of function will we use to represent revenues? I know. How about y equals 140x? You don't have any constants because you get exactly $140 per helmet and that's it. So we want to know where we break even. In other words, what is the value of x of which y is equal to 0? The profits are equal to 0 is what I should say. So we set the total revenue is equal to the total costs. So we set these equal to each other, and there you go. If we sell 12,500 helmets, the cost of production will exactly match the revenues. So therefore, we want to sell more than this because every extra helmet will bring us another $140. Now, if I plug this 12,500 into the revenue function and the cost function, I should find that they're equal to each other. All right, so let's do that. So the costs of producing 12,500 helmets are $1.75 million. And the revenues received from doing this would be the 140x. Okay, so therefore, let's plug that in and make sure that we're getting a revenue of 1,750,000. And it is the same. Now I went ahead and graphed. Now again, this is Excel. Maybe we'll do this in Symbolab. It doesn't look so great, but you can see that they do intersect when y, yeah, this is terrible. Y is 175,000. All right, let's do this. Y equals 140x and y equals 120x plus 250,000. Oh God, what happened? Nah, something's not right. There's no way that that's what this is supposed to look like. These are both vertical lines. What is wrong with this thing? No, I don't know. I'm losing my faith in this thing again. All right, well, we'll stick with Excel. You can see that if we make 12,500 units, you can see it. What the hell is that? Okay. All right. So that's how that worked out. So it was just kind of an interesting way of seeing how to determine where the two lines cross. In this case, it matters a great deal because it's telling us what our break-even point is. Now, as far as the company is concerned, after this, if you notice the blue revenue line is greater than the orange cost line. So up here we have positive profits if we keep producing more helmets. But if we are unable to sell more than that number of helmets, down here it's the other way around. So we have profits are negative. That's why this matters so much to the company. If they discover that they're unable to sell this many helmets, then they should probably close their doors. But if they can sell more, then they'll make money. And this is how they determined it. Beautiful. All right. Well, you know what? We just finished chapter 2, I see. Well, that changes everything, doesn't it? Because you know what that means. Now you are able to do this chapter 2 problem set. I didn't realize we were going to get that far. So it is right here. It's on Moodle. If it's not, I'll put it there. You're being asked to find equations of lines and determine whether, oh, that's all you have to do. This shouldn't be, oh, wait a minute. Okay, well, it's a little trickier than I thought, but yes, you're definitely able to do this now. So once you, between now and next Wednesday, work on these problems. Now, 3 is next. 3 is polynomial and rational functions. They're a little bit messier than what we did in this chapter. And oh my God, I forgot. This is where we are going to review complex and imaginary numbers. It's kind of an interesting topic. So we'll get that out of the way, and then we'll dive into other functions like quadratics, and there's the vertexes that you saw in Symbolab, and it's not quite as scary as it looks. You probably have all been exposed to the quadratic formula anyway, so we'll be using that pretty extensively. We'll be finding, as usual, ranges and domains. So no, this will be pretty good. So we got, you know, oh, is that, oh, okay. So in other words, if we kept scrolling, it would have looked normal. Okay, I was just very concerned because it looked awful. So, all right, apparently Symbolab didn't do a terrible job here. We just weren't looking at it at the right scale. So that's good. Okay, I will now have faith again in Symbolab for a while. All right, anyway, I guess it's getting pretty late here. I guess we better get out of here. You can only take so much in one day, I'm thinking. We don't want your brains to actually catch on fire, which they will if we keep doing this. So we'll stop here. And so your job between now and next week is to work on the chapter 2 problem sets. Also, of course, make sure you understand what we did in the first set of problems, the first 3. Go through the solutions, see if you can reproduce them without looking at the answers. And if you still aren't happy, take a look at Khan Academy, because he has everything, as we've seen. All right, so if there's no last minute questions, I think we'll stop for today. And I'll see you all as usual next Wednesday. All right.
Yeah.
So go have some fun, do something else for the rest of the day.
Have a good day.
Thank
Plenty
you.
of hard thinking for one day. All right. See you later.
Thank you, Mr. Anderson.
All right. Bye. Oh.